about Quaoar. Greetings everybody, welcome to yet another episode of the Dwarf Planet series. We'll be focusing on the dwarf planet Quaoar, which is a very unusual dwarf planet because it has a lot for us to study and we haven't yet understood much, but in this video we're just going to unpack what scientists have managed to unpack as they were studying this dwarf planet. So let's get on to it. We'll start as always with the Kepler's third law, where we're going to look at the orbital period and the semi axis as our main variables, and we're going to derive equations using Kepler's third law. And the expression for Kepler's third law, as we can see, t squared over r cubed is equal to 4 pi squared over gm, and you can just follow through and see how we arrive at the period in terms of the semi axis and the semi axis in terms of the period. Okay, now we're looking at the semi axis. So as we know, the semi axis is half of the longest diameter of an ellipse, and we also have what we call a semi axis, which is half the shortest diameter of an ellipse. That should be the square root of the sum of the aphelion and the perihelion. If you watch, I think, the Pluto video, you will get to see how we calculate the semi axis. We don't focus on it much because most of our calculations involve the semi axis, which is more of the let me say radius of the orbit. But in this case, we're going to look at that diagram, the illustration that we have. We have those two Quaoars on either side, and we have a P and an A, which is the aphelion and the perihelion, respectively. Or rather, not respectively, but as you can see, with the yellow being the aphelion and the blue being the perihelion, it's respective when you then look at the derived equation, which is that is equal to A plus P, which is aphelion plus the perihelion, over 2, and it's with the respective colors so that you can see what we mean. So that's where we get those values: 45.488 plus 41.900 over 2, which is the average, and that's where we get the semi axis in astronomical units, which is 43.694 astronomical units. And then to convert to terameters, because we know that tera means 10 to the power of 12 in terms of indices, and also it being the prefix of a unit. And then we know meters is the standard unit for length according to international standards. So we can see that 1 meter is equal to 6.685 by 10 to the power negative 12 astronomical units. So what we do is we got our astronomical units for 43.694, then we divide that by the astronomical units equal to 1 meter, so that we find the terameters for those astronomical units, or for the 43.694 astronomical units. And we then find that the quotient will be 6.5361 terameters, which is equivalent to 6.536 terameters to 3 decimal places. And then another way to find the same value is by using the terameters for both the aphelion and the perihelion. As you can see, we average them, divide by 2, and then we will still get the same or similar answer. If we put it to 3 significant figures, it will be 6.54 terameters, which will be the same with the previous that we got, but in this case there's a difference of 0.001 terameters. So yeah, that's a slight difference. That's when we then use average to see the accurate value to use. But that's basically the concept of how we calculate the semi axis. Now in the beginning we saw the Kepler's third law, and it's written there at the bottom there. So now I want to look at how we calculate the period, and one equation which we can use, or one formula we can use, is the one of which is derived from Kepler's third law, and that's t is equal to 2 pi multiply it by the fourth root of z cubed, which is the semi-jet axis cubed, over g, which is the gravitational constant, multiplied by m, which is the mass of the larger mass, which is the mass of the sun in this case. So we then find that the period, we substitute the values z with the semi-jet axis 6.537 by 10 to the power of 12, which we calculated in terameters. Now we just put in power of 10 to the power of 12 because of the tera. Then we cube that, and then we divide that by the product of the gravitational constant. You can see the value there, and the mass of the sun, which is 1.989 by 10 to the power of 30 kgs in kilograms. We use kilograms as the unit, the standard unit in our calculation. And then our t, which is the in Earth years, which is the period in Earth years, will be 9,114,589,275 seconds. It's in seconds. And then we divide that by all those numbers, the product of all those numbers, 60 seconds by 60 minutes by 24 hours by 365 and a quarter days, which are the days in the year. If you need those explanations of why we're doing that, you can watch the previous videos from the other planets and dwarf planets to get the explanation of why we are doing it like that. But this is basically a shortcut. There's a long way of doing it. You will find the video, the link in the description for the YouTube channel of the video where there's the longer version of this calculation. So when we convert, we then find 288.8239 when we divide those values into the billion seconds. So we then find our period being approximately 288.8 years, correct to one decimal place. So that's the period in Earth years for Quaoar. It takes a very long time to orbit the sun. So just get to understand that. So it means that it takes 288 years, while the planet Earth, the one we are stepping on, it takes only 1 year to go around the sun. Quaoar needs 288.8 years to just go around the sun once. So it's really a slow planet. Okay, so as you can see, we're now looking at eccentricity. But just a side note, Quaoar is in orbit around the sun, as you can see in that diagram at the top left there. But that diagram does not reflect the true eccentricity. So it means the orbit is bulging out a lot more than usual, than the actual appearance of the orbit. Although we know that the orbit is invisible, it's just a path that we assume the planet will be moving in according to our calculations and our estimates in the scientific world. But we find that things can change because these things are natural. They are not consistent and they are not stationary. They can shift positions. Any event can disturb their movement. So, but for now, we just know that our orbit has this eccentricity that we're going to be looking for here. But just bear in mind, the orbit is not white in color. It's invisible. It's just a path that we draw to reflect what is actually happening in space. So you can read that note at the top there about what eccentricity is, so that you get an understanding of what we're doing when we're calculating. Okay, so don't lose this when you're now looking at this. So we see the formula for eccentricity. It is the A and the P. We saw the A and the P just previously on the orbital period and the semi-jet axis diagrams. We saw what the A is, the aphelion, and the perihelion, and we see where we get those values for the A and the P. So we then plug in those values into that formula. As you can see, 45.488 is aphelion over the perihelion, which is 41.900. That's in the denominator there. Then we add 1, and then we divide into 2, and then we subtract from 1, and then we get 0.04106, which is approximately 0.041123 significant figures. Just so you understand why this formula is like that. If the aphelion and the perihelion in this case are equal, like in the value, if the magnitude is the same for the aphelion and the perihelion, if they divide each other, they'll give you 1. If you add to that 1 in the denominator, you get 2. If you divide 2 into 2, you get 1. If you subtract the 1 outside the bracket and the 1 that you get inside the bracket, you get 0, which means the eccentricity, which is in the form of epsilon, according to what you see there, is just a symbol that we decide in the science field to use for our eccentricity. So if we subtract 1 and 1, we get 0, and then that becomes the eccentricity of the orbit or the ellipse of a planet orbiting the sun, when that orbit is circular in shape, if it's a perfect circle, we expect the eccentricity to be 0, because 1 minus 1 will be 0, and that's because the aphelion and the perihelion will be equal, and if you put in that equation, you get your eccentricity equal to 0. Just something so that you can think and try to understand and conceptualize what's happening, and so that you can visualize what we're talking about. So we now move on to probably the easiest of the calculations that we're going to cover, which is the common formula or equation for density, which is density is equal to mass over volume. And as we can see, we have the conversion rates below there at the bottom left rather, which is 1 kilometer is equal to 100,000 centimeters, and 1 kg, which is kilogram for mass, is equal to 1000 grams. And as we can see in the calculations, we did not convert with the rates as we did with the Umea. I think with the Umea we did convert each value, the mass and the volume. We converted them into the centimeters and grams so that we could use that unit, grams per cubic centimeter, which is what we're going to use here, but we're going to do it differently this time. So we just divide the volume into the mass in terms of their kilometers and their kilograms, as you can see. So it to be cubic kilometers rather into the kilograms, and then we get that value, which is 1.675978 by 10 to the power of 12. I stand to be corrected, but that should be in kilograms per cubic kilometers. And as you can see, 1 kilogram per cubic kilometers is equal to 1 by 10 to the power negative 12 grams per cubic centimeter. So that's the rate we're going to be using to convert that density into grams per cubic centimeter. So what we do is we multiply with that 1 by 10 to the power negative 12, and then that means it's should be 1 picogram per cubic centimeter, because 10 to the power negative 12 is equivalent to the prefix pico, which is like the inverse of tera, the terameters that we're looking at. So that's what I wanted you to just see. Okay, so that's how we then do it, and we get 1.675978 grams per cubic centimeter, and that should be equal to equivalent to 1.68 grams per cubic centimeter, correct to 4 decimal places. So this is fairly the easiest calculation, which is the density of Quaoar. Okay, now we look at Quaoar's surface gravity, and that's a very popular quantity, gravity. So let's get into it. So we're going to look at 2 laws that were gifted by a very talented scientist called Isaac Newton. So Isaac Newton gave us the law of universal gravitation, and he also did give us the second law of motion, where a body of constant mass, its acceleration is directly proportional to the resultant force applied on that mass. So that's why we have that mg, because we are using g instead of a, because we're looking at acceleration due to gravity. It's specific. So we find that if the gravitational force is equal for both, with the mg and with gmm over r squared, it means that we can put those equations together as simultaneous equations, and then we can find the final equation, which is g, small letter g, is equal to big letter G, which is the gravitational constant multiplied by the larger mass. In this case, the larger mass, as you can see in that diagram there, we have a white dot, which is the point mass on the surface of Quaoar, and because it is on the surface of Quaoar, it's going to be the one experiencing that acceleration due to gravity. But even if it's above the surface, as long as it's in the gravitational field, it can feel the pull of the gravitation. This is why even when you jump up into the air on Earth, you fall down to Earth. It's because Earth is pulling you, it has some gravity. Yeah, it might seem not to be practical in terms of applying this gravity in terms of common sense, but it's how we have gotten to understand the nature of this pull that draws us to Earth, and why when we escape the atmosphere we won't be able to feel that. So it's something that we can rely on for now, until we get maybe a better explanation of why we fall down to Earth after jumping into the air. But yeah, nonetheless, let's focus on what we're looking at, which is Quaoar. So Quaoar is going to be the big letter m, which is the mass of Quaoar, and our small letter m would have been cancelled out. Remember, like terms cancel out in the equations, summatation equations, and that small letter m was the mass of that dot, that white dot on the surface of Quaoar in the diagram there. It can be any color, it's just an illustration for now. So that's how we look at it. And then the separation of the masses is r, and it's squared according to the equation which is derived from Newton's law of universal gravitation. So we substitute the values in there. As you can see, the gravitational constant, we have seen that value many times, multiplied by the mass of Quaoar, which is 1.20 by 10 to the power 21, divided by the radius of Quaoar, which is in this case is the separation of the masses, because we're going to assume that all the mass of Quaoar is at the center, right at the middle of Quaoar, inside Quaoar. I needed a cross section of inside Quaoar showing the core and the like, but you can watch the Umea video, the Earth video, I think in the Neptune video if I'm not mistaken. Those 3 videos I explained that how that line travels inside and what it means. It's just an illustration. There's no line that cuts through inside it to show the radius in real life. It's just something for you to understand the concept. So which means that radius, as you can see, will be in meters, because we're using standard units here. So that one is in meters, and the mass is in kilograms, just for you to take note of that. So it's 543,000 meters squared, or square meters. So we then find it being equal to 0.27162378, which is approximately equal to 0.27 meters per second squared to 2 decimal places. So that's the gravity on Quaoar, which is very small. As you can see down there, it's around 2.8%. And as you can see, we just put it as a fraction to that of Earth, so that you can see, we can compare the gravity that we feel on Earth compared to on Quaoar. So which means you might maybe take time to fall down on Quaoar when you jump up than on Earth. And Earth, it's like an instantaneous event. You just jump up, you come back down quickly, and you'll feel the impact. You might even hurt yourself, and yeah, it's a terrible feeling for those who have experienced that. So 2.8%, that's pretty low compared to that of Earth. By the way, 9.81 meters per second squared, that's the acceleration due to gravity on Earth, for those who haven't gotten that. So that's why we have used it there, just so that we compare with that of Earth. So it's around 2.8%, the magnitude of gravity on planet Earth. It's very, very small for that. And also it being a dwarf planet, kind of makes sense. So yeah, let's move on. Okay, so just look at the diagram that's there and read whatever you're seeing in front of you, so that you get to understand what we're going to be looking at next, which is Quaoar's geometric albedo. I don't want to waste much of your time by making the video lengthy, so just to cut the video short, just pause and read whatever you see, and then we'll continue from there. Just pause, read, and then you press play, and we'll continue from there. Right, so I hope we have gone through that. If you haven't understood anything on those explanations, I hope you can just find time to go through the previous videos again and get to understand the concept. But now we just continue because of time. So we have our albedo as A, which is equal to that bracket there, 1329 by 10 to the power negative 2.737, which, as we see on top there, it's the H, which is the absolute magnitude Wimband of Quaoar. And then that's why we have on the diagram the DQS, DQO or DOQ, and DOS. Those are the 3 distances we use to find that magnitude, absolute magnitude of the brightness that's being reflected, or the light that's being reflected from the sun by Quaoar. Okay, and then that is divided by 5, and then we put it over 1086, which is the diameter of Quaoar. And then we put all that into the brackets, and then, or parentheses, depending on how you call them, and then you multiply by 2. Rather, not multiply by 2, but you put it to the power of 2. Sorry for that. And then we get our answer as 0.12039, which is approximately equal to 0.120, correct to 3 decimal places or 3 significant figures. So that's basically the geometric albedo. And as you saw, 0 means pitch black, and then 1 means a perfect reflector. So we just use the scale between 0 to 1, which means this one does not reflect a lot of light. And as you are going to see later on, There are some explanations for that from the scientists and their use of the Hubble telescope, which took some images, and they're able to analyze what's going on the surface, which gives the rise to this or the decrease in this albedo. Okay, so now we move on to the black body temperature of Quaoar. Just take time to also verify the information you find here so that you get a better understanding, and so that you can check and balance these values that we are seeing here, if they are balanced equations, or we're just playing with your mind. Hopefully we're not playing with your mind, but anyways, this is how we calculate the black body temperature. We have the geometric albedo, the star luminosity, and our star is the sun in the solar system, and then we have the Stefan Boltzmann constant and the semi-major axis. Those are the main unknown, rather main known values that we are going to be substituting into that equation that you see at the bottom there under those variables, which is T is equal to, and don't be confused by that T. That T is the thermodynamic temperature, not the period. We used T as the period previously, now we're using it as the temperature, so don't be confused. The reason why we use T also in period is because T would represent time, and period is based on time. That's why it's expressed in seconds or years, as we then saw later on. It's based on time. So the temperature is equal to the fourth root of L, which is the luminosity of the star or the luminosity of the sun, which is at value 3.828 by 10 to the power 26, multiplied by the difference between 1 and the geometric albedo of Quaoar and the geometric albedo of a perfect reflector. And as you saw, Eris is probably the one which, if there's another one, then you can also put in the comment section, but Eris is one which is very, very close to 1 in terms of its geometric albedo. So we then divide that product by 16 pi multiplied by the sigma, the small letter sigma. We're using Greek letters here. You find that there are many Greek letters like the delta, that rather not delta, the rho that we used for density. We use that one as rho. It's not a p, it's a rho. And then here we're using sigma, which is the Stefan Boltzmann constant, which is around 5.670374419 by 10 to the power negative 8. And that units, I can't be reading that. It's like watts per meter squared by kelvins to the power 4, something like that, which is multiplied by the semi-major axis. And remember, we're using meters, which is the standard unit, so it's in terameters here, which is 6.537 by 10 to the power of 12 meters. So we have to convert them to meters. That's why we have to put the 10 to the power of 12. And then we square that. As you can see, it was z squared in the equation, which when we do the entire calculation, we get 40.7761, which is approximately equal to 40.8 kelvins to 1 decimal place. You find that with temperature, we usually put it to 1 decimal place. That's just like the standard. So that 40.8 kelvins, that's the temperature in terms of thermodynamic temperature. But now we want to, which is in the standard units, we use kelvins as our standard unit. So it's not degrees Fahrenheit, it's not degrees Celsius, it's in kelvins. So now I want to put it to degrees Celsius, because I know most of you are familiar with degrees Celsius. And then for those who use degrees Fahrenheit, you can do conversions. Even for the other videos, you can do that conversion for yourself. Just find the conversion rate from kelvins to degrees Fahrenheit, and then you do your conversions. Or even if you use any other type of unit, just find the conversion rate and use that value 40.8 kelvins to put it into your own system, because we use the metric system, and we have the kelvins in that system. And then since our absolute zero is equal to negative 273.16 degrees Celsius, if we look at the pressure temperatures graph, if we extrapolate it, we'll find that at absolute zero, where there is zero pressure and zero temperature, we find it's around negative 273.16 degrees Celsius. So our temperature will then use theta for that one, just to differentiate between the degrees Celsius and the kelvins. So we subtract we will subtract 273.16 degrees Celsius from the 40.7761 kelvins that we saw, and then we find our value in degrees Celsius, which is negative 232.3839, which is negative 232.4 degrees Celsius. Correct to 1 decimal place. Like I said, it's just the standard that we use. So that's the temperature for you. Very cold. We don't have that on Earth. We probably have around 20 something degrees Celsius as our standard temperature there on Earth. You can confirm with the Earth video, which is on the YouTube channel or in the series or in the podcast. So we then find that this dwarf planet is really cold, and it's probably not suitable for life to live there. When I mean life, I mean organisms. Yes, so we don't expect organisms to be living in such conditions. These are very harsh conditions, not harsh conditions as in hurricanes on Earth and the storms on Earth and drought and whatever that we experience on Earth. When we mean the harsh conditions, we're meaning this type of harsh conditions on Quaoar, where the temperature is more than 100 times worse than what we experience on Earth. So yeah, it's very, very tough that we may have to see which planet is best to go to, and Mars has been selected as the one. But yeah, it's a talk for scientists to have as we try to explore our universe. This universe is really, really big. If you realize how big the universe is, you feel so useless. But yeah, you're not useless. You are just tiny, a very small grain in the universe. So just appreciate the fact that you're actually existing. Now this is for those who are just very curious and are trying to work out the unit. For those who didn't know, you can actually work out the unit of the magnitude or of the quantity. So that's how we find our kelvins, using the equation. You can still use the equation to work out the unit, only that you have to remove the certain constants. Like you see, the 16 pi is not there. It's because it's a constant that is unnecessary. We're not looking for the value or the magnitude. We're not looking for the unit. So we just deal with units, and that constant is removed. So yeah, that's how we get to work that out. If you don't understand, you can just visit the other videos, the previous videos, so that you can get a better understanding. But if you can follow through on what's happening, you can clearly see what's being done here until we get to that fourth root of those cancelled W's and that kelvins to the power 4. So it's the fourth root of K to the power 4, which is equal to K, which is kelvins. Very simple and straightforward. So I hope you have enjoyed the calculation sections. As always, just get to understand the language of the universe, which is mathematics, and just get to familiarize yourself with what we are doing on Shumbafoot. And very soon we'll be celebrating the 8th anniversary of Shumbafoot, a very important event, just not to miss out on. So yeah, just do something on the day, help someone, show some love to people. Just as Shumbafoot has been trying to help you, also try to share and help others from what you've benefited on Shumbafoot. Not to market Shumbafoot, but just to do something good for the people around you, so that they also benefit in the same way that you're benefiting on this idea of Shumbafoot. That's helping you to enhance your knowledge and be in a better position of understanding the things of this universe and the things of this world, and yeah, just so that you are a better person in life. Yeah, you don't want to be an ignorant person who's just useless or good for nothing. Yeah, so at least you're getting this information just for your own benefit. You can choose to use it, you can choose to dump it away. There's no problem. It can be rubbish to you, garbage in, garbage out, or you can try to use it in whatever you want to do. It's up to you. All I have to do now is to leave it up to you to follow what I've been lecturing you on in terms of this calculation section. Enjoy the rest of the video as you get to understand more of Quaoar, and stay tuned for more from Shumbafoot, even as we celebrate our 8th anniversary. Happy anniversary in advance. Till we meet again next time. Cheers. More on Quaoar. ya Quaoar.